Welcome to the central force problem. Today we are going to discuss the differential equation for the orbit and integrable power law potentials. Our parameterization of the central force problem gives the radial and angular coordinate of the particle as functions of time with initial conditions fixed by the conserved values of the energy and of the orbital angular momentum. Our objective is to obtain the equation of the orbit, namely to obtain the radius as a function of the angle, for instance. And we can pursue this starting from the conservation of angular momentum. Namely, we can take this expression, solve it for the differential of time, and then what follows immediately is that we can write the derivative with respect to time um, in terms of the derivative with respect to the angle. And as such, if we take this into the equation of motion corresponding to the radial coordinate, we immediately obtain the orbit equation in the form given here. However, things can be taken a step further by using the substitution u equals 1 over r and using the fact that the force is derived from a scalar central potential, the orbit equation can be worked in a simple way to in order to be brought to the form given here. What is important to note is that in this form the equation is invariant to a reflection of the angular coordinate. That is, the orbit is symmetric around two adjacent turning points. If the turning point is taken at theta equals 0, the reflection is obtained under the transformation minus theta goes into theta, to which the orbit equation is invariant. Also, the initial conditions are unaffected by this transformation. That is, the value of u at theta equals 0 and the fact that its derivative with respect to theta vanishes at this point both remain unchanged. Therefore, the orbit is invariant under reflection around the apsidal vectors. Thus, the entire orbit can be retraced if half of it is known, that is, the portion between two turning points. Another approach involves using the conservation of energy. So from equation 317 and using the result that we have deduced from the conservation of angular momentum, we can immediately solve for the angular differential to obtain the result here. And this can be immediately integrated up to a constant in order to formally give a result. Furthermore, if we once again employ the change of variables here with u given as 1 over r, then we can bring theta to this expression, and in principle, assuming we can perform the integral, which usually can be quite problematic, then we can invert the relation and then invert the transformation in order to obtain r as a function of the angle. Now, the most important potentials are power law functions of the radius given by such expressions, such that the force will vary as the nth power of r. The exception to this is given by n equals with -1, as this leads either to no force at all if the potential is 0, or in case if the potential is 1 over r, then this is a situation characteristic of a line source rather than a point source. So it's a situation more common, for instance, in electrodynamics, where it could have, for example, a charged wire generating a force field. In any case, from results 337 and 338, we can obtain the expression given here in the specific case of potentials varying as power law functions of the radius. Now, for integrals of this type, circular solutions to the orbit equation are found for the free values of the coefficients listed here. Circular solutions means simply straightforward solutions of the integral given in terms of the standard trigonometric functions. However, for a more general class of coefficients, namely the one given here, and for some fractional exponents, a solution can be given in terms of so-called elliptic functions. And many other exponents lead to solutions in terms of hypergeometric functions, which generalize the previous two classes of solutions. And if analytical methods fail, numerical integration is always possible for non-pathological potentials. Now, with specific regard to elliptic integrals, they have the general form given here, where r is a rational function of x, so it's essentially just a ratio of two polynomials in x, and omega is the square root of the quartic form given here, where obviously alpha and beta cannot simultaneously be zero, because in that case we would simply end up with a circular solution to the integral. And the result 347 leads to this type of integral for the following power laws, the ones listed here, using the change of variables u equals with x to the power rho, where rho is the one given here. So it's very easy to check that for these particular combinations of coefficients, the integral given here is always of an elliptical type. As an application, consider the situation where a particle is describing a circular orbit under a central force, with the condition that the center of force is situated in a point located on the circle. So the parametric equation of a circle of radius r0 in terms of Cartesian coordinates is the one given here, and we will choose the reference frame such that the center of the circle has the coordinates here. So x0 equals 0 and y0 equals r0. And for this choice, then it follows immediately that the square of the radial coordinate of the particle is just 2 times y times r0, and the y coordinate is simply r times sinus of theta, just due to the usual transformation from Cartesian to polar coordinates. So what we obtain immediately is the functional relation between the radius and the angle, or the orbit, as given here in equation 1. Then if we bring this into the expression of the orbit equation and simply work out the derivatives and all the calculations involved, it follows that the nature of the force is such that the force is attractive, and it varies as 1 over r to the 1 over radius to the 5th power. And what this will imply immediately is that the potential varies as 1 over the radius to the 4th power. Then by going back to the to equation 1, so to the orbit, if we just take its time derivative, we obtain the expression here. And then if we use this together with the conservation of angular momentum, we can write this equation for the square of the radial velocity. And this, together with our expression of the potential, leads immediately to the conclusion that the total energy in this case is 0. Furthermore, once again, using the conservation of angular momentum and the expression of the orbit, we can calculate the time it takes for the particle to perform a full circuit around a circle. And this is done by a simple integration which can be carried out immediately if we use the trigonometric identity given here, and this is the result, which depends on the mass of the particle, the radius of the circle, and the angular momentum. Furthermore, if we go back to the time derivative of the orbit, we can write the components of the velocity in Cartesian coordinates as being given here, and we can write the magnitude of the velocity as given here. And notice that in the limit where the sinus of theta goes to 0, so in the limit where the particle crosses through the center of force, all three of these quantities go to infinity. So the situation is presented here. This is the potential that we have obtained, and for the specific case of the total energy being 0, notice that the particle is essentially doomed. It cannot escape. It can move until it reaches the potential barrier, and then it will go back and collapse on the center of force. So, in summary, we have derived the differential equation for the orbit and have studied its symmetry properties. We have investigated its general application to power law potentials and have established classes of analytical solutions, which are the circular, the elliptic, and hypergeometric functions. As an example, we have studied its use on a force varying as the inverse fifth of the distance to the center of force. And in the following, we will discuss conditions for closed orbits together with Bertrand's theorem. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.